Alright, so this is our AP Chemistry Chapter 16 lesson video. This is part 4, and in this video I'm going to cover section 16.7 and 16.8. So hopefully this one will not be as long as the previous one, part 3, but you never know. We'll see. Depends on how many times we can make assumptions when we're doing ice charts. Alright, so before we were talking about acids, and so we discussed how the generic reaction for an acid is HA yields H plus plus A minus. And then we said so that makes the generic K expression to be H plus times A minus over HA. Okay, and so that's what we used in our last video. Alright, and so this works for acids. Bases, on the other hand, it's a little bit different because remember, a base accepts a hydrogen, in this case from water, so we do have to put water in the formula. So we put B for base plus water gives HB plus. Every now and then you'll see this as BH plus. It just depends on what you're looking at. HB plus plus our OH minus, which of course is what makes it a base. And then the K expression for a base is the products of reactants, just as always. So HB plus times OH minus over just the base, because remember, water is a liquid. Pure liquids and solids are not included in the K values because the concentration can't change. You only include either aqueous or gases. Alright, so obviously, hope you're ready. We're going to be doing some ice charts again. So, if you're not getting good at ice charts yet, you'll still get some more practice. So let's look at the first one together. So it says calculate the concentration of OH minus in a 0.1 molar solution of NH3. And it gives me Kb equals 1.8 times 10 to the negative 5. All right, so for this one, I set up my B plus water yields my HB plus plus OH minus. All right, so I just set up my ice chart. All right, so we're trying to figure out the concentration of OH minus. All right, so we want this number right down here. Alright, so it tells me I'm starting with 0.1 molar. Oh, sorry, 0.15 molar. I can leave out my water because, of course, my water is a pure liquid. It doesn't tell me I'm starting with any products, so I put 0 for both of those. Alright, and then, of course, just like in acids, we subtract X from this side. We add X to my products. So this becomes 0.15 minus X. This becomes X, and this becomes X. Alright, and so then next I set up my Kb. Now in the beginning I'm going to write the expression, but then after this one, just know it so I can just go ahead and start plugging in. Alright, we don't want this video to be 50 minutes like the last one. My gosh. Alright, so we have HB plus times OH minus over just my base. Okay, remember I don't want to include water because it's a liquid. So I plug in my Kb, which is 1.8 times 10 to the negative 5. Oh, and that's one thing I do need to point out, y'all. You've got to make sure they give you the correct one. Okay, they could have given me Ka instead, and then I can't plug that in for this. Okay, we'll look at later in this video how to get in between Ka and Kb if you need to. It's kind of like going in between pH or POH. Alright, and so then my HB positive is X. My OH minus is also X, so I'm just going to put X squared over my 0.15 minus X. But my Kb value is very small, so I can make my assumption. So, ooh, thank goodness. So I can just assume this is about 0.15. And so then I just solve for X. So when I solved for X, I ended up getting 1.64 times 10 to the negative 3. Remember, my unit is molarity. X is OH minus, which is what it asked me for. And so that's my answer. Okay? So really, the better you get at ice charts, like doing them quickly, then the less daunting they are. Okay? You just got to get to where you can do them quickly. Like, do you know your initial amounts and you're subtracting and adding X? Do you know your final amounts and then you know X and you're working backward? We'll get to some today where we're looking for this initial amount, but we might know some other stuff. Okay, so you just plug in what you know and solve for what you don't. That's pretty much all you do for it. So hopefully that one wasn't too bad. So now let's see if you really thought it was that bad, because you can try the next one. So for the next one, you will need your book. If you don't have a book, you can look it up. But you need, for this one, let's see, what did I pull from the book? Okay, the book apparently does give us KB values. Okay, so you need KB values for these things. Okay, so you can just Google like a KB chart or even a KA chart. But I haven't shown you how to change between the two, so if you already know how, you can use that. All right, so I'll assume you've already done this and you tried it, and let's look at it together. So for pyridine, it's asking which of the following compounds should produce the highest pH as a 0.05 molar solution. So y'all, highest pH means the most concentration of OH minus. So one thing I can look at is this is an acid. Acids have lower pHs, so I know automatically it's not nitrous acid. That has a low pH. When I look on page 691 in the book, I find out pyridine has a KB of 1.7 times 10 to the negative 9. And then I find out that methylamine has a KB of 4.4 times 10 to the negative 4. So remember, we talked about this in the previous video. The larger the Ka value, the stronger the acid. Well, the larger the Kb value, the stronger the base. So which one's bigger, 10 to the negative 9 or 10 to the negative 4? 10 to the negative 4 is bigger, so that means my methylamine is the strongest base and will produce the most OH minus. Okay, and because it has the largest Kb value, that means it favors making products, which the products for bases include OH minus. Alright, so next, types of weak bases. So we've already talked about what the strong bases are. They're the alkali metal with hydroxide, or the heavy alkaline earth metals with hydroxide, which is C8, Sr, and B8. So what are the weak bases going to be like? Well, the most common weak base you'll see is NH3. We use that one a whole lot. So one is neutral substances with a non-bonding electron pair to act as a proton acceptor. For example, NH3. Amines, which have NH bonds, are weak bases. And then the anions of weak acids. So we know HClO is not one of the strong acids, it's a weak acid. So if we take that conjugate base, that would be a weak base. Just like that. A lot of times on the AP exam, though, they usually tell you. They'll be like, oh, blah, 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 a weak base. But NH3, you definitely need to know that one. All right, so let's look at our next one together. It says a solution is made by adding solid sodium hypochlorite, which is just NaClO, to enough water to make 2 liters of a solution that has a pH of 10.5. Calculate the number of moles of NaClO that were added to the water. The Kb value is 3.3 times 10 to the negative 7. Wow, I gave myself a super lot of room to work this out. So I'm going to start down here, and I might have to kind of go on the side again, like I had to do yesterday. All right, so we set up our ice chart with what we know. All right, so they told me I made 2 liters. The solution has a pH of 10.5. pH is not helpful, but from pH, I can get to OH minus. Okay, I can also get to H plus, but H plus isn't helpful. I don't have H plus in this. All right, so I'm going to take my pH and get to OH minus first. So what I did was I went ahead and did POH is 14 minus pH. And so I got 3.5. And then I said, okay, well, OH minus is 10 to the negative POH, 10 to the negative 3.5. And I got 3.16 times 10 to the negative 4 molar. Okay, so remember, we said when they tell you pH, that is assumed in equilibrium. Okay, so this 3.16 times 10 to the negative 4, that is my equilibrium concentration. Because these are 1 to 1, it also has to be my equilibrium concentration for this one. Since it didn't tell me I was starting with any, I can assume I've started with 0. And since water is a liquid, I don't care about it at all. We always just cancel water out. All right, so obviously to get from 0 to this, that meant my change was this. we actually don't know the starting amount, so that's actually my x. Okay, so up until now, we've always been given the starting amount, but they don't have to give you the starting amount. Here, they're asking us, how much did we have to use to make this? Okay, so we got to figure out the starting amount. But I do know I'm going to be subtracting this much from it. And so my final or equilibrium amount would be x minus that right there. Okay, so remember, once you have your whole row of your equilibrium amounts, whew, that's a crooked line right there. Once you have all those, then you can use your KB to solve for x. Okay, so I'm just going to go ahead and plug in. So KB, or 3.3 times 10 to the negative 7, equals my HClO, which is 3.16 times 10 to the negative 4, times my OH minus, which is 3.16 times 10 to the negative 4, over, and so then don't forget here, we don't use water. Okay, we don't use water because it's a liquid. Over my x minus 3.16 times 10 to the negative 4. Alright, and so then I'm not going to show you how y'all should be able to do basic algebra. You multiply this over here, don't forget to distribute, multiply these, and you solve for x. So when I solved for x, I ended up getting 0.303 molar. And that's, of course, for ClO negative. It didn't ask me about ClO negative, it asked me about NaClO. But I can see this is 1-to-1. Remember in one of our previous videos we had talked about like, oh, but this could have been like a 2, like this, and then it's not 1-to-1. It's 1-to-1, so this is the concentration of the NaClO. Alright, so I have my concentration of NaClO. I know how much is 2 liters, so I can solve for moles. So we know, here, I'll just do it up here, moles equals molarity times liters. So my molarity is 0.303, whoop, my decimal got kind of crazy there, times my liters, which is 2 liters. So once I did that, I got 0.606 moles of NaClO, just like that, okay? So on this one, I had to do an ice chart to figure out something, so then I could use my molarity equals moles per liter. Alright, so hopefully that one wasn't too bad. Like I said, we were just solving for an initial concentration this time. All the ice charts work the same. And for some reason, it seems like y'all struggle more with the base ones. I don't really know why. Like, they work the same as the acid one. Alright, so y'all try this one. I'll assume you paused it and tried it, and let's look at it together.
Ms. Ann Miller, please make contact with the front office. Ms. Ann Miller.
Alright, so it says a solution of NH3 in water has a pH of 11.17. What's the molarity of the solution? And it gives me the Kb value. Alright, so I'm going to just use my generic formula. Remember, you can write out, or generic reaction, you can write out the actual reaction if you want to. So again, we want to know what is the molarity of the solution, so I don't know what I'm starting with. I know water's a liquid, so I know I don't care about it. It gives me pH, so I can figure out OH minus. Alright, so I did POH is 14 minus pH, and so I got 2.83, and then I said, okay, well OH minus is 10 to the negative POH, which is 10 to the negative 2.83. And I got 1.48 times 10 to the negative 3 molar. Alright, and so that goes in for my OH minus, but at equilibrium. And because these are 1-to-1, it goes in for this one too. Now let's just pretend like this had been a 2 in front. Alright, that means I would make double the 1.48 times 10 to the negative 3. Alright, we started with 0, so that means I just added this much. That's all I did. Whoop, my plus sign got kind of crazy there. And then from this side, we subtracted. So once I have my equilibrium values, I can use my KB. Okay, so it gave me KB, so KB, or 1.8 times 10 to the negative 5, equals my HB, 1.48 times 10 to the negative 3, times my OH, which is also 1.48 times 10 to the negative 3. You could have just squared that if you wanted to over my b, which is x minus 1.48 times 10 to the negative 3. Just like that. All right, and so then all I did on here was just solve for x. So I got that x equals 0.123 molar, and that is for my base, which my base in this case is NH3, which is what it asked me about. And so that's my answer. That's all we got to do. All right, we didn't have to do any quadratic equations, so that's a positive. Let's hope it stays that way. We'll find out together, I guess, as we keep going. All right, so now let's talk about the relationship between Ka and Kb. So Ka times Kb has to be Kw. And so if you remember from the previous video, Kw is 1 times 10 to the negative 14. So Ka times Kb must equal 1 times 10 to the negative 14. So what that means is if one goes up, the other must go down, because together the product has to be that number. As the strength of an acid increases, which means the larger Ka, the strength of the conjugate base decreases, which means a smaller Kb. This formula only works for a conjugate acid-base pair. So like if they gave you HCl and NH3, you can't compare Ka and Kb for those. These are not a conjugate acid-base pair. Remember, you know it's a conjugate acid-base pair because it differs by 1 hydrogen. So like for example, I could do this formula for HCl and Cl negative. So see, this is a conjugate acid-base pair. I could do it for H2SO4 and HSO4 negative. This is a conjugate acid-base pair. Remember, they differ by only 1 hydrogen. All right, so let's look at some super easy examples. Oh, just kidding. We're going to look at another formula first. So, of course, we all know P means negative log of. So if you do the negative log of each, then your pKa plus your pKb must equal pKw, which is 14. Okay, so pKa plus pKb equals 14. Ka times Kb equals 1 times 10 to the negative 14. Both of these formulas are on your formula sheet, so don't worry about memorizing them. All right, so let's look at the first one together. So it says the base dissociation constant Kb for the fluoride ion, calculate it, if for HF, Ka is 6.8 times 10 to the negative 4. Okay, so I know that Ka times Kb is 1 times 10 to the negative 14. So if I'm looking for Kb, I obviously just divide both sides by Ka, and then I just plug in. So it's 1 times 10 to the negative 14 divided by my Ka, which is 6.8 times 10 to the negative 4. All right, and so once I divided, I got 1.47 times 10 to the negative 11. And remember, K values have no units. All right, so I mean, doesn't get much easier than that, right? So let's look at the bottom one. It says the acid dissociation constant is what we're calculating for the ammonium ion. And then they gave us Kb. Okay, so down here I'm trying to calculate Ka instead. All right, so again, we have Ka times Kb equals 1 times 10 to the negative 14. This time I'm looking for Ka, so I divide both sides by Kb. And then I just plug in. So it's 1 times 10 to the negative 14 over my Kb, which is 1.8 times 10 to the negative 5. And don't forget, y'all, here I should have put them up here too. How a lot of you type it in the calculator, if you divide by one of those powers of 10, you need to put it in parentheses. All right, so just make sure you're always getting the right answer. So I got 5.56 times 10 to the negative 10. And again, Ka and Kb have no units. Any of the K's have no units. Well, equilibrium K, capital K. And if we're talking about lowercase k for rate law, that does have units. And if you don't know what I'm talking about, go back to chapter 14, because that's where I covered rate law. All right, so you try these. For this one, again, you'll need to either A, use your book, or B, look up the KAs for these. Like in the book, they only give us the KAs. So you would look up the KAs, and then you'll decide from there. For this one, you don't need to look anything up. So I'll assume we've already done that, and now we'll look at it together. All right, so it says, which of the following anions has the largest base dissociation constant? So in other words, they're asking for the largest KB. But in the book, it only gives me the Ka values. So here, I'll give you what Ka values I found. So for NO2 negative, I found that Ka, so these are all the Kas, is 4.5 times 10 to the negative 4. This one, the Ka is 4.2 times 10 to the negative 13. And this one, the Ka is 1.9 times 10 to the negative 5. All right, so remember, as Ka goes down, Kb goes up. Okay, so in other words, the lowest Ka equals the highest Kb. So I'll look at my choices. So I need to pick the smallest. So I have a 10 to the negative 4, 10 to the negative 13, and a 10 to the negative 5. This is my lowest Ka, so that's going to be my highest Kb. So it will be that PO4 with the negative 3. All right, so part B, hopefully you figured out how to use that super simple formula of pKa plus pKb equals 14. So it says the conjugate acid of the base quinoline has a pKa of 4.9. What is the base dissociation constant for quinoline? Okay, so we know that pKa plus pKb equals 14. So here I have pKa, I'm looking for pKb. So So we're just going to do 14 minus the pKa, which is 4.90. So I got 9.1. But y'all, this is pKb. Notice it didn't say what is pKb. It says what is the base dissociation constant. That means I'm just looking for straight what is Kb. All right, so the way we go opposite of negative log is 10 to the negative power. So Kb, whoop, that's a P. Kb is 10 to the negative 9.1. And so once I plug that in, I got 7.94 times 10 to the negative 10. And no units because it's a K value. All right, so hopefully you got that one right. A lot of people on this one, the first time you see it, you'll stop at the 9.1. Okay, but remember, if it asks for pKb, 9.1 is fine. But if it asks for Kb, you then have to do 10 to the negative 9.1. All right, so hopefully y'all got those right. Or if you didn't, hopefully you at least understand what you should have done now. All right, so that one wasn't nearly as long as our last one. All right, so again, y'all, the thing I would recommend is just getting good and comfortable with ICE charts. You will probably not see a lot of ICE charts on the actual AP exam. Maybe 1 or 2 questions even need them. Some of them, you get so good at them that you can actually kind of do the ICE chart in your mind, and then you forget you even actually need the ICE chart. Okay, but until you get to that level, just make sure you work them all out, fill in what you know, solve for what you don't know.